Um, yes, so I'll be talking about the lower food web and some of the results that we have. And so just a kind of a quick overview, I'll be talking about things that you probably expect to hear in this talk. We'll be touching on spring chlorophyll, zooplankton, mysis, benthic invertebrates, some nearshore to offshore patterns, and some seasonal patterns. A couple of these, spring chlorophyll and mysis, are reported to be particularly important for understanding forage fish production in the lake in a Fish Commission report a few years ago. So jumping right into this is some offshore chlorophyll data from the spring, and this is from the Muskegon region. In the early 2000s, as quagga mussels were proliferating in the lake, we lost the spring phytoplankton bloom, that spring diatom bloom. And you can see since that bloom disappeared, there's some variation in our spring chlorophyll levels from year to year, but there's really no return of that spring bloom in the offshore region, and 2025 was no different. Next, this is some remote sensing data. This is provided by the EPA and Michigan Tech, and it's more seasonal data, and it's a lake-wide basis. But you can see along the bottom axis there how over time we've lost our spring bloom. And then you can even see in the more recent years where that oligotrophic conditions, they're even creeping into our summer months based on this remote sensing data. Next, we'll look at some nearshore data. The nearshore is much noisier, much more difficult to get a handle on. There's a lot more variation across space within the lake, and there's just a lot less data from the nearshore, even though clearly it's an important region to understand. This data is from the area between Muskegon and Grand Haven. Of course, the Grand River is a very important source of nutrients for the lake, so it captures that area. You can see in this time series, there's a lot of variability in our spring chlorophyll from year to year, but 2025 was well above the average that we've seen for the more recent data, and it was comparable to what we saw in the mid-90s. So fairly high chlorophyll concentrations in this area in the nearshore last year. We can also look at the seasonal chlorophyll to get a sense of how the nearshore and the offshore vary over time. This is from those same regions that I just showed for the nearshore and the offshore. And you can see that really high spring pulse of chlorophyll in the nearshore in May, whereas in May, that's the lowest chlorophyll that we see in the offshore when we should be seeing a spring bloom. It's interesting to see as you go on into the season, the nearshore and the offshore might not be that different during the summer months. We have somewhat less sampling in the shoulder months than we normally would, but you see that difference between the nearshore and the offshore here. Chlorophyll doesn't also just vary from space nearshore to offshore or location to location. It also varies within the water column. And so this is the vertical profiles of chlorophyll derived from fluorescence profiles. And you can see in the spring, it's pretty well mixed. There's no spring bloom there. And it's pretty well mixed during that time period. We're still isothermal. But by June, that deep chlorophyll layer starts to build. In July, we had fairly high chlorophyll levels in that deep chlorophyll layer, although it's a fairly narrow chlorophyll layer compared to what it could be, but we have almost 5 micrograms per liter there, so high chlorophyll in that deep chlorophyll layer in July. And then by September, that layer is starting to disappear, and that's pretty typical. It's just pretty ephemeral feature right there, but very important during the summer. Next, jumping into some of the zooplankton data. This is lake-wide data during the summer, and it's provided by the EPA Glimpo cruises. And you can see that there were some declines in zooplankton over time in that early 2000s period. But over time, there's been a rebound to some extent in zooplankton biomass in the offshore region. And in particular, over the last 5 years, there's been pretty strong contributions of Daphnia. That's that red in the graph. Daphnia is a large-bodied cladoceran, and if you have high contributions of Daphnia, that reflects fairly high secondary production relative to if you have a high calanoid copepod, that's the blues contribution. So if you have a lot of calanoid copepods, that reflects a more oligotrophic condition. So strong Daphnia reflects more food up in the upper water column and higher secondary productivity, whereas those calanoid copepods, they're more prevalent in the lower levels of the water column, and that's more oligotrophic. conditions that they would reflect. We also have zooplankton from our Muskegon area. This is from the near shore on the top and the offshore on the bottom. And this is just the summer data. And you can see that in 2025, we had relatively high biomass of zooplankton at both these sites. In fact, since 2007, that's the highest biomass of zooplankton that we've had at our offshore site. And if we look at both those sites on a seasonal basis, you can see at the nearshore site on top, that really high biomass is just based on what one time in August when we had really high biomass in August. But at our offshore site, that high biomass that we saw was really sustained throughout our summer sampling. And again, it seems really driven by high biomass of Daphnia, which reflects high secondary production and high food resources up in the upper part of the water column. Next, I wanted to take a look at some zooplankton data in an area that's very near shore. And we don't get a chance to talk about this area as much, but I pulled some of the data off. This is data from the beach. So we're talking less than 1.5 meters deep, right? Waders territory, not big, large vessel. And so this is from Muskegon, and it's the zooplankton data during our March through June Carriganine sampling. And then the whitefish sampling that's shown here is from our Newston net in the same area. The whitefish sampling doesn't go as long as the zooplankton data because once they get big enough, we quit using the Newston and switch to the beach seine, but you can't really show them together on the same plot. But I just wanted to show how this area where these whitefish are when they're hatching and after they first hatched and they're growing, just how variable that zooplankton abundance can be from year to year. You see it's all over the place in 2022. And then we see years like 2024 where we had relatively high zooplankton numbers compared to maybe 2025 and 2023. Also shows how variable from year to year that the whitefish abundance can be in these areas where we have a couple years, 23 and 24, with high numbers of whitefish, and 22 and 25 where we had much lower numbers of whitefish. And I've just started looking at this, but it certainly does seem like there is the possibility that there's a mismatch between when these whitefish are out there and when the zooplankton is highest. And at this Muskegon site, with the highest catches in that Newston net are fish that have just lost their yolk sacs. So this could be particularly an important time. And I'll take a better look at the full data set for this coming up here. But I just wanted to show that there are other areas in the open water that are important and definitely important areas for fish. I also wanted to highlight how temperature can be a really important factor on the whole food web, and in particular, what happens in the winter. And we often overlook winter because, well, we just don't really work that much from December through April on the lakes. We have a thermistor mooring that we occupy year-round off Muskegon, about 10 miles from shore in about 110 meters of water. And over the last 12 winters, we've had an extremely cold winter, a couple of them, and a few extremely warm winters, and then everything in between. But I just wanted to show that what happens in the winter affects the rest of the year. So on the bottom left here, I show that the average winter temperature, so from overturn until the lake stratifies again the next year, there is a strong relationship between the cumulative degree days that you'll have during this next stratified period. So what happens in the winter is affecting your temperature in the stratified period the next year. And then on the bottom right here, there even is a relationship between that average winter temperature and the overall average biomass of zooplankton that next year. So warmer winters have somewhat higher zooplankton biomass that next year. So there's really a lot going on in the winter that we don't know about, but we probably should. Next, jumping into one of those important indicators, the mysis. This is some summer data from the Muskegon sites. Going back to 2007, it goes back a little bit further. But in 2025, we had the lowest mysis densities at that offshore site that we have since 2007. We had been seeing kind of an up and down it's definitely in the depressed area of that pattern. We also have some mysis data on a lake-wide basis collected by a whole host of partners, not only from Lake Michigan, but from 3 of the other lakes as well. And you can see, compared to the other lakes where we see that huge decline over time in mysis in Lake Michigan, and it remains depressed in 24, 25 in this plot. Whereas in the past, mysis densities should have been comparable between Michigan, Ontario, and Superior to some extent. Now, Michigan is much more comparable to Lake Huron and very depressed compared to where it should be. I know a lot of people here maybe have never seen a diparia, but I don't want us to forget about these. When, when I started this, there were 10,000 diparia per square meter in a lot of the areas. So this plot starts even after the decline, right? So it's this is from the Southern Basin surveys that take place, I think, every year or every other year. Already, the declines are already underway in this plot, and it's by different depth zones. And you can see as they crash, they reach, basically they're gone. And so that inset is just so we can see the little noise that's happening from year to year. For that survey in 2024, there was a little bit of a bump up. The only good news in that survey is that they were found at 5 sites instead of just 1 in that Southern Basin survey. But essentially, diparia are very, very rare in the lake. From that same Southern Basin survey, this is quagga mussel density, again by depth zone. You can see that in some of the mid-depth areas, quagga mussels really shot up high, and then they came down. Other areas, such as the deepest area in red on there, the quagga mussels just built up to where their biomass, and then they've just stabilized out. But overall, at all those depth zones, there's some noise from year to year, but it really appears like quagga mussels have landed in a more stable zone from year to year. Not to say that they're low, they've stabilized at a pretty high level, but we aren't seeing the huge pulse like we saw when they first came in at some of those depth zones. So we have a more stable quagga mussel population just at a fairly high level. And I just want to note that the CSMI lake-wide survey by a whole host of partners, especially EPA and Buffalo State, along with NOAA, the lake-wide survey will be taking place this year. It was supposed to have taken place last year, but it will be taking place this year. And then just to touch base on the veligers, these are the larval quagga mussels. And it's interesting to see these are 3 sites at different depths off of Muskegon. And for the most part, over the last few years, we've seen very low densities of veligers. The net type used in this would be the larger veligers, so they're pretty close to settling out. But we've seen fairly low densities of these veligers over time. Not that there aren't a lot of them, especially when they first come out. But it is good to see that there aren't a whole lot of them relative to some of these years where there were just a ton of veligers. Veligers are a potential food source for larval fish, but maybe not necessarily a good food source. As Ralph alluded to, that'll be one of the focuses of understanding what these larval fish, alewife and perch, are eating in the spring, and how, if they're eating veligers, how that's affecting their energetics. We did a little bit of work this past year, and it seems that veligers are probably 3 to 4 times lower in energy than just ambient zooplankton. So we'll see if that plays out, but that would certainly suggest they're not a great thing to eat. So just kind of wrapping up what we saw, this was kind of a year of paradoxes. We had no spring bloom in the offshore, but we had higher than average chlorophyll concentrations in the nearshore. That just highlights how different our nearshore and our offshore are now in the lake. We also saw really high biomass of zooplankton, especially in the offshore. That certainly doesn't seem consistent with a more oligotrophic lake, right? But remember, a lot of things affect zooplankton. Temperature, top-down effects, as well as the bottom-up effects. So that does seem somewhat paradoxical, and it was largely related to those Daphnia, which suggests there were fairly high food resources for fish up in the upper part of the water column. On the other hand, mysis are at a depressed level, and of course, dipraea are virtually gone in the lake. So keep in mind that probably is setting some real bounds, even with high zooplankton, without low mysis and without dipraea. That's certainly affecting this production of fish that we can see in the lake. Of course, the mussel biomass is stable but relatively high. And I just, again, plug for this winter ecology that we need to have a better understanding of what's going on in the lake the whole year to understand the lake. And if there's any questions, I'd be happy to try and answer them.